Hello everyone, my name is Meng. Today I'm going to present our work on the NeuralEcho hybrid of full-band and sub-band recurrent neural network for acoustic echo cancellation and speech enhancement. Here is a typical scenario of the echo cancellation. We have a near-end speaker, and now the speaker is playing back the far-end signal. And that signal is captured by the microphone as well, so that in the microphone it receives a mixture of the near-end signal S and a far-end signal FX. Here F includes loudspeaker, nonlinear distortions, echo paths, reverberations, and signal. A typical single-channel echo cancellation network input based on the input single-channel microphone and single-channel far-end reference. By taking the short-time Fourier transform, we can compute the features like a log power spectrum. By doing the feature fusion, we send the feature embedding to the AEC layers, and finally we try to estimate time frequency domain mask. It can be either real mask or convex mask. That mask is multiplied to the input microphone signal to reconstruct the near-end signal. So what's new in our work? First, feature extraction. We leverage the second-order statistics across the signal channels, microphone channel and far-end reference channel, and time and frequency domain correlations. Second, formulation. By generate intermediate estimation channels. So the single-channel problem is converted to a multi-channel problem. So therefore, a cross-channel second-order statistics can be used to estimate multi-channel enhancement filters. It's like beamformer or NVIDIA beamformer. Third, the model. We have a self-attentive sub-band GRU model to perform AEC on the multi-channel, the microphone channel, and the intermediate AEC processed channel and echo estimation channel. Finally, we build an all-in-one model and support the test as like AEC, denoise separation, reverberation, and automatic gain control. We also add the speaker information to further improve the performance. And finally, we unify the single channel and the multi-channel into the training so that the model can support various member microphone channels. So here's the model diagram. So the input is X is the far-end reference channel, and Y is the microphone channel. We stack up the two channels to form the vector Z. By computing the second-order statistics across the channel, we have a feature phi t, and across the time we have a feature phi t, and across the frequency we have a feature phi f, and also plus the log power spectrum of the microphone signal Y and the far-end reference signal X. By doing the feature concatenation and the linear projection, we have a feature beside bar, and that one is passed to a full-band GRU network, and the output is passed to two individual convolution, 1D convolution layers to estimate a mask for estimating AEC process channel. The ME is multiplied with echo far-end reference channel to estimate echo. Although it's not a supervised train here, we just presumably assume that this is the AEC process channel YA and the echo estimation channel XE, and together with the input microphone signal Y, so we have we convert the original single channel problem Y to a three-channel problem. So, and then furthermore, we compute the log power spectrum on the YA and the XE, and together with the previous feature psi bar, we do the feature concatenation and pass to a linear projection layer and another full-band GRU layer. After that, it goes to 6 individual 1D convolution layers to estimate 3 masks for extracting the target speech from the 3 channels, and 3 masks to extract the noise signal on the 3 channels. So here the noise means near-end noise and as well as the residual echo. So eventually we have 3 channels of the noise estimation and 3 channels of the target speech estimation. So we can compute the noise covariance matrix and the speech covariance matrix by doing the feature concatenation, and goes to layer normalization, linear projection. So here we combine the dimension on the batch and the frequency together, so that from here it's a subband processing. So each frequency band is processed independently. It goes through a multi-head attention and subband GRU and another multi-head attention layer. Eventually, after linear projection, it estimates 3 channels of the complex weight. That weight W is multiplied with the 3-channel signal Z tutor to reconstruct the target near-end signal. The full structure of the NeuralEcho model, it achieves the SSNR and task and whatever reach. By comparison, we just remove the subband layer structures and just increase the dimension of the full band layers, such as the computation complexity are the same, but we just estimate the YA as the echo cancel signal and apply the loss function on the YA here, so that we have a full band model. We see that performance degrade a lot compared to the subband model. Second is by remove the Y from the 3 channels, just to use the YA and the XE. We see that performance is slightly degraded. Third one is by removing the XE from the 3 channels, and just to use the Y and YA in the following computation. We see that performance drop a lot. That means the so-called echo estimation channel are important for the following multi-channel processing. The last one is by removing the attention, performance is slightly degraded. By adding the speaker information to extract the features to help the network to better extract the target speaker from the mixtures. We see that usually the microphone receives the signal, it has a weak energy, so by adding the AGC branch, so we still have the NeuralEcho model here. In the output, a computer loss function on the pre-AGC branch with the target as a reverberant clean signal. And the output goes to another GRU layer and to estimate a post-AGC signal. And that signal is used to compute the loss function with a dry clean post-AGC signal. The AGC branch does both the dereverberation as well as the gain control. So we use our in-house AGC tool to process the original dry clean data and generate the post-AGC dry clean target signal for the training purpose. Here is an example. The microphone signal is like this.
Sleeping at night activates the resting and testing the greater part of the day in the air.
The mixture is Chinese and English. English is a fine signal. Chinese is near-end signal. By the NeuralEcho model, the output is like this. By using the NeuralEcho model with AGC branch. For comparison, we just use the output of the NeuralEcho model and send that to a conventional AGC tool, and for the energy boosting, the background noise is boosted. Another innovation is the loss function. So here is an example. The first row is a spectrum of the microphone signal, and the second row is a far-end signal. And the last one is a near-end signal. And we can see that in the blue bounding box is a double talk session, and the green bounding box is a single far-end talker session. Estimates the target here in the single far-end talker session is all zero. By considering loss function SICR, there are the target signal in the denominator. So if the target signal is all zero, there's some singularity problems. So in order to avoid the singularity problem for the SCR loss, so we have to filter out those data that allow the far-end, single far-end durations, talk durations. By doing that, we lose a certain number of data, particularly the far-end single talk samples. Here we propose a new loss function by incorporating a parameter gamma. Gamma is a proportion of a time in a training segment that is occupied by the silence from the target output related to the total duration of the segment. So if the target is like all zero and the gamma equal to 1, the loss function just depends on the magnitude ms L1 loss between the target and the estimated spectrum. So if target is not all zero, it combines the two loss. So here is a comprehensive experiment by comparing the NeuralEcho with the conventional AEC and Swift AEC, neural network-based model like neuron Kalman filter, and the frequency and time domain ASTM model. Here is by incorporating the Swift information. The performance is slightly improved. By adding the AGC branch, whatever reads is significant drop. So here for the with the AGC enabled, we're not computing SICR and the test because we computed SICR and test based on the reverberant clean target. But I see that AGC branch does the dereverberation, so for a fair comparison, we just not show complete the SICR and the test for the neural network model with AGC branch. Finally, we just use the new loss function with the single and double talk ratio dependent parameters. It achieves the better result. Finally, to extend the model from one mic to any number of mics. So just simply in the input, it converts from the Y to a Y1 all the way to a YM. M is the number of mics, and plus the far-end reference channel. So here in the internally, the V tutor is Y1 from YM and also YA1 from YAM, and plus the echo estimation channels. In the training, we just use a placeholder for 8 channels, but for each training samples, we just randomly to zero out a random number of channels, such that the model, after training, the model can support any number of the mics, input mics. We see that for the 1 mic and 2 mic, there's slightly degradation compared to the original single channel NeuralEcho model, but it becomes better since 3 mics. And also the clear trend is with the increasing of the number of mics, the performance is improved. Here is an example. The input is and the target is. And here is a 1 mic NeuralEcho model and process on a 1 mic signal. See there's some like residual noise here. So here is a 8 mic model, just to train a model for supporting just the 8 mics, and the process on the 8 microns. It serves as upper boundary. The bottom 2 output are the unified model and process the 1 mic and process 8 mics. Okay, that's all. Thank you very much.